In this lesson and the next few lessons, we're going to apply the knowledge and skills we've learned about finding linear graphs and their rules to practical problems. This area of our work is called linear modeling. To start off with, we need to think about slope again. Now, some people think about slope as rise over run, and you've heard me say in class I don't like that. I like people to decide, is the slope positive first or is the slope negative? And once we've made that decision, we know what sign the slope is, and then we draw ourselves a right angle triangle between two known points on the line, and we work out a size for slope. That is the vertical distance divided by the horizontal distance. Another way of thinking about that vertical distance is it's the rate of change of y compared to the change in x. So the change in y with respect to the change in x is a rate. To give an example, if I had a set of axes, say y, and the y actually represented the length in kilometers and the x-axis represented time in hours, then the gradient of any straight line on that graph would be the change in kilometers compared to the change in hours. That's called kilometers per hour, that's speed, and so that's a rate. So if we can look at a practical situation we're trying to model and we can find a rate of change, that's going to be useful for us to find a rule. That's the rule we've been using. Now sometimes we're told something about a situation that happens right at the start, and often this is called the y-intercept. When we're dealing with things that change with time, this is often called the initial condition. It'll be whatever the thing is at the start of the experiment at time equals 0. And so if we can get these two pieces of information, we can write down a rule, a linear rule for the situation. If we have the gradient and any other point, just the gradient with one other point, we're also able to find the equation of the straight line because we can figure out what A is. And of course, if we've got 2 points that lie on a straight line, like 2 key points that we know are linear in our model, we can use them to work out our gradient using a gradient triangle, and then we can use the math we learned earlier to find A by substituting one of the known points into the rule because it makes it true. The other thing to bear in mind when we're doing linear models, often we change the name of our pronumerals so that they're appropriate to the situation being modeled. For example, if y was distance, I might use lowercase d, or if x was time, I might use lowercase t. Let's look at a simple example with tomato plants so we get the idea. Alright, let's say someone wanted to look at how a tomato plant grows. The same plant in a pot at the start, after 1 week, after 2 weeks. And let's say at the start the plant was 5 centimeters high, and whoever was measuring these plants did it at the end of each week, and they did it for 10 weeks. Now we're going to model this situation as a straight line graph. If we look at this, we can see that it sort of looks linear, doesn't it? We can fit a straight line across the heights here. So a linear model seems okay. In fact, they would have collected enough data to be able to figure out that the way the plant was growing, it was a constant rate of change of 6 centimeters a week. So the first thing when we do a linear model is we need to define our variables. The y variable is going to be called h here for the height of the plant in centimeters. The x variable is going to be called t here for the time in weeks after it was planted. And the model y equals a plus bx will become h equals a plus bt. When t was 0, h was 5. And that's the y-intercept, if you like, in this case the h-intercept. So a equals 5. So we also know that they collected data every week and they noticed that it was growing at a rate of 6 centimeters a week. So the rate of change is 6 centimeters a week. Notice now that the slope has units of measurement associated with it. The change in y, in this case h, is measured in centimetres, so that's at the top, and the change in time measured in weeks is at the bottom, so it's centimetres per week. So the model for our tomato plant is H equals 5 plus 6t. Now, when we do linear modelling, our normal straight lines go on forever in both directions. They're not restricted. But in real life situations, in a lot of modelling situations, we do want to restrict them. In this case, we did this experiment, whoever did this experiment did it for 10 weeks. So one of the things we could say is that the time for our experiment is restricted between time equals 0 weeks and time equals 10 weeks. And so our model is really good for making predictions within this period of time. Let's have a look at the sketch of this model. Alright, so I've got the axes here, labelled H and T. We'll put some more labels on them in a minute. Now the y-intercept, the h-intercept, is 5, so we're going to start with our first point there. That occurs at time equals 0. Now I could use my slope, and I will in a minute, but I'm going to look at what happens in 10 weeks. In 10 weeks time, t would be 10. 6 times 10 is 60, and 60 plus 5 is 65. So in 10 weeks time, my plant is going to be 65 centimetres tall. And I can fit a straight line to this. Now that's our model for our tomato plant. So I might put a heading, tomato plant. I should also put some more information on the axes. H is height, and it's in centimetres. And T is time, and this is in weeks. And I forgot to label my point here, so I should do that now. That's the point 0.5. It was 5 centimetres high when we started the experiment. And so that is a sketch which shows two key features. It's got lots of information. I'll put a heading up here, tomato plant, probably growth I'd add, I reckon. And label it with the rule. There's my label. And what if I didn't notice that this experiment went for 10 weeks? How could I have found a second point? Well, like we did before, the gradient or slope is 6. And we want to write that like a fraction. So we started off knowing the height of the plant initially was 5 centimetres. So we're going to draw a right angle triangle from there. So if we go across 1 and up 6, that'll give us a new point, and that would be a second point if I didn't realise that the experiment went for 10 weeks. And that second point would be located at 1 week, and 5 plus 6, 11 centimetres in height. So it doesn't really matter. If you've got those two key features for your initial sketch, it doesn't matter. This matters once you realise that there is an endpoint. These are called endpoints to our model. Now, if I use my model to make predictions, that's the whole purpose of modelling things, to make predictions. Let's say I was interested in how high the plant is after 8 weeks. So I can take my model, h equals 5 plus 6t, and replace time with 8. 6 times 8 is 48, and 48 plus 5 is 53. So my plant will be 53 centimetres tall. And I should always, when I'm doing these word problems, don't just leave it with the maths, but actually write a short sentence so that people know you've answered the question. Now, when we make predictions using our model within this area where our model is valid, it's called intra, meaning within, polation. And it's a pretty safe bet. So if your data is pretty linear, using prediction within the range of your data is fairly good, and it's called interpolation. We'll learn more about this later. What if I use my model to make a prediction outside the range of values? Well, when I do that, it's called extra, meaning outside the data collation. And I might do this in two ways with this plant. I might be interested in how long ago it actually was a seed, and I could, take this back this way and say, okay, how many weeks ago? That'll be a negative number, but in the context of the problem, I might predict so many weeks ago its height was 0, it was a seed. In fact, let's do that little bit of working out here. If h is 0, 0 equals 5 plus 6t. Change the side, change the sign. So if I move that 5 across, it becomes -5, and divide everything by 6. So the prediction would be less than a week ago, minus 5/6 of a week ago, or 5/6 of a week ago, my plant was a seed. Now, extrapolation is not as reliable. And if we use our common sense, we could probably think, okay, when things are initially growing, they probably don't grow at a linear rate. They probably grow faster than that. And so when we do extrapolation, there is a bit of risk about the validity of our prediction. But that's the elements of setting up a model. And in some more lessons, I will do more examples for you to get used to it. So this initial lesson is just to get you the idea of the elements we need to write. You'll also find this in your student notes.